W represents the weight associated with the hidden layer neurons. CJ stands for the center of hidden layer neuron, and S stands for the spread of hidden layer neuron. So CJ and SJ are related to the radial neural network or function. So in order to calculate or estimate the unknown wind speed, first we have to take various inputs, say PM, omega t, beta. We have to form a set of inputs. Say if you look at the block diagram, so what I did, first I have fixed omega t and beta. I have varied the PM from one value to say infinite set of values. Similarly, in the second set, what I did, I have chosen PM and beta constant. I have varied omega t from one fixed value to another set of value. And in the third set, PM and omega t I had kept fixed, and beta I have changed from one set value to another set value. So this is how all the range for PM, individual inputs, PM, omega t, beta, that is maximum power coefficient, omega t blade turbine speed, and beta is the blade pitch angle. All the range of the values of PM and omega t and beta, they are covering all the range. Individual ranges are being covered. So that is why if you and then after calculating all the set of values, its corresponding VW, that is wind speed, was calculated, and such a system was designed. I had taken help of MATLAB Simulink, as well as I had taken help of MATLAB programming to have all the set of range of input, and its corresponding VW was formed. And finally, after the artificial neural network, taking into account of radial basis function, it was trained in a proper manner. After it is being trained in an offline mode, then it was run in an online mode to in such a manner that if you are giving any value, PM, omega t, beta, any value, if you are giving any combination, then you will be getting the exact, or you can say approximate value of VW. So this is the thing which was done in this whole thing. So here you can see that the data set was first generated by varying wind speed, then by varying speed command only, and then lastly varying only the step load of DOIG. So this is how we are we are giving a wide set of variation of PM, omega t and beta, and its corresponding VW was calculated. Then it was trained with the entire range of the three inputs and the output, the RBFN, and utilizing the RBFN function, the artificial neural network was trained, and finally it was ready to predict the wind speed. Now we are having the on the screen we can find, okay, just a minute. So here we have on the screen we can find a simulation model of radial basis function network based wind speed estimation. So here we can find this is the ideal wind turbine, where we are giving the three inputs, that is turbine speed, actual pitch angle, that is beta, wind speed VW, and then we are getting the turbine torque. Then it is given to this is a block diagram representation. Then we have the blade, then we have the hub, and here we have the turbine speed hub. Then we have the gear with the help of hub speed it is being connected, and then we have the induction generator and load, and this is being connected to a summing point. And then we have a pi controller, proportional plus integral controller. Then we have an actuator and the actual pitch angle. Now this is an open loop system. To make it a closed loop system, this actual pitch angle is being continuously taken and is given as an input to the ANN, artificial neural network, where we have incorporated radial basis function. So beta is continuously being fed, What about omega t? Omega t, whatever omega t we are getting, turbine speed that we are getting is continuously being fed to ANN and also the PM. So PM is calculated from here. PM is being calculated. So PM, omega t and beta, the real values, the real all the real values which you are getting is given to the trained ANN system, that is artificial neural network, where we are incorporating radial basis function, and then we are estimating the wind speed, and then we are using the maximum power extraction algorithm, which is based on MPPT, that is maximum power point traction algorithm. And then this power is being fed, this power is being fed over here, and then we are finding out the speed error. This is giving us a reference speed omega t star. This is omega t. So this is how we are getting the speed error. Now proportional to the speed error, again the actual pitch angle is being generated. So this is how at each and every instant the actual pitch angle is being generated, which is proportional to the speed error which we are generating. So this is how the whole system, the closed loop system, is working. So this is a simulation model, right? So here, so as we have discussed earlier, the RBFN based, that is radial basis function network based ANN system, artificial neural network, we have been designed, which is estimating the wind speed, which is further incorporating the maximum power extraction algorithm to obtain the reference wind speed, and this reference speed is compared with the real value so that we can get the speed error, and proportional to the speed error we are generating the pitch angle, which is further incorporating the ANN to generate the wind speed. So this is how we are having the whole closed loop system. And if you talk about the values, so here in the table you can see whatever the values we have chosen, these values we have taken. Now these values have been, these values are the actual values of a wind turbine which are taken, but all these values are in per unit system. Like these, this first three is representing the inertia of blade, inertia of hub, inertia of generator. Then the next three is representing the damping coefficient of blade, of hub, of generator, and the last two is representing K, that is spring constant between blade and hub, spring constant between the generator and the gearbox, GG, that is generator and the gearbox. This is how these values have been chosen for calculation. And yes, this is the most interesting part of the session, that is results and discussion. So case one, when we are estimating the wind speed for constant wind speed profile, if I am assuming that the wind speed is not going to change, it is remaining constant, so how does the estimated wind speed look like? So you can see if I'm choosing one per unit, so this is the one per unit actual wind speed, the upper one, and the lower one is the estimated wind speed. So you can find some little bit of error is there. If you're choosing 0.9 as actual wind speed, and this is the estimated wind speed, so here also some error is there. And if you're choosing 0.8 as actual, and the upper one is representing the estimated wind speed. Similarly, 0.7 if you are choosing the actual, and the upper one is the estimated wind speed. So you can find here also little bit of error is there. So these outputs have been taken from the ANN output. So here we can find little bit of errors there. This is for constant wind speed profile. Now next, so these are the errors at 1 per unit, at 0.7 per unit, at 0.8 per unit, and at 0.9 per unit. So you can find the error is very less, of the range of 0.02, something like that, but not much more than that. Then we are having a variable wind speed profile, because wind speed is not remaining constant, it may vary. So we need to check our system for variable wind speed profile also. So here we have taken a ramp wind speed profile. So here you can see the actual wind speed is at 0.7, and then it is taking a ramp shape. Then it is switching to 0.9. So 0.7 to 0.9 it is switching and is taking a shape like this. So the actual one is like this, and the estimated you can find little bit of deviation, but here it is almost same. Little bit of deviations are there. So if you calculate, so actual and estimated wind speed in per unit, and this side we are taking the time in seconds. So like 30, 32, 34, these are the time in seconds. Now, if you find out the error means the actual wind speed minus the estimated wind speed. If you find the error, this is the error. So error is again very, very less. Error is again in per unit versus time in second. Next, we have another shape, another type of wind speed profile, that is another ramp wind speed profile. So here also the wind speed is at, say we are assuming it is at 0.7 per unit, and it is taking a shape of a ramp. It is fixing at the 0.9, and then again it is falling down and it's coming down. And so this is the actual wind speed. And estimated wind speed you can find somewhere it is almost same, and somewhere little of error it is giving us. So it's error, it's corresponding error. If you calculate, that is actual minus the estimated one, you will find the error is like this. So error in per unit is to time in seconds. So error is also again less. Now we are having another wind speed profile, that is a sinusoidal wind speed profile, where we are assuming that the wind speed is following a sinusoidal profile. Okay, and so you can find 0.8 to 0.9, then 0, 0.7, then 0, then again 0.9 to 0. So this is the actual one, and estimated you can find, this is the estimated one. So somewhere it is matching up, and somewhere it is giving a small error. So if this error, if you're finding out, you can find the error is like this. So here also you can find error in per unit with respect to time in seconds. If you find, here also the error is very, very less, of the range of 0.03 per unit, which is very small. So this is how we can, in brief, we can say that for wind speed estimation, if you are using a ANN system, which is based on radial basis function, so you are able to get the estimated wind speed in a which is in a manner which is almost nearer to the actual wind speed. So here we have the conclusion of our session. So a radial basis function network we are using. So a radial basis function network which we have designed and trained, it is used to provide nonlinear input-output mapping. Obviously, the input and output, there is a nonlinear mapping is there for wind turbine aerodynamic characteristic. And number two is the RBFN, that is radial basis function network, is first trained offline. It was first trained with the set of input and output. It was trained offline based on the mechanical power, turbine mechanical power, that is PM, turbine speed, that is omega t, and blade pitch angle, that is beta. As the training data set consists of the entire operating range of wind turbine, as we have discussed how we have chosen the data training data set. So as the data set is consisting of the entire operating range, the resulting RBFN system is helping us to provide us the accurate wind speed estimation. Though we are having a little bit of error, still the wind speed which we are estimating is almost same as the actual wind speed. So about the results which we are getting, which we have discussed in the results and discussion section, we have found that the estimated wind speed is almost same as the actual wind speed with a negligible error for both constant. We have checked for the constant wind speed as well as we have checked for the variable wind speed profile. In both the cases, we have found that the actual and the estimated, between them, a little bit of error is there. So now what are the references? So these are the references, the different papers which are taken into account for the research purpose. Whole thing was the output which I got is for that MATLAB Simulink as well as MATLAB programming was taken help of, and these were the references taken. So thank you so much for your patience hearing. So now if you have got any kind of question, you are most welcome to ask. Anyone want to ask something? Okay.
No, ma'am, no
Yes,
questions.
no one is going to ask anything. Okay, let us finish the session. So thank you so much for your valuable hearing and patience hearing. Thank you. So this is how I'm concluding.